now we'll look at heat and work individually. For heat, which is an exchange of thermal energy, we are measuring this in temperature. So, temperature is a measure of the thermal energy in the system. So, if we look at kind of an example, if you had a cup of hot coffee and you put that coffee on the counter and you let it cool down all on its own, the coffee cools to a lower temperature. And the way that it does this is by transferring thermal energy to the surroundings. So the thermal energy that was contained in the high temperature of the coffee to start is transferred out to the surroundings, and as a result, the coffee goes to a lower temperature. Now, the reason that you don't feel warm air around the coffee, right? Because the air around the coffee is absorbing all of that thermal energy, but there's a lot of air around the coffee and the air is moving. So it's going to absorb some thermal energy and then continue on, right? We can only look at our processes in an isolated fashion, and right, that has too many follow-up things that happen. So where you might feel the thermal energy on the table, but you're not going to feel it in the air. Thermal energy always transfers from a high temperature to a low temperature, right? You would, if you put a hot cup of coffee out on the counter, you would not expect the surroundings to get colder while the coffee gets hotter, right? The natural flow of thermal energy is from high temperature to low temperature. And this will happen until you reach thermal equilibrium. And things are in thermal equilibrium with each other when they're at the same temperature. So the temperature that you end up at will be somewhere in the middle, and that is the point of thermal equilibrium. To calculate heat, this depends on the change in temperature, and it depends on the identity of the substance, right? So delta T, that's to be expected. This thermal energy transfer, we're measuring it with temperature. It goes from high temperature to low temperature, but the identity of the substance, that we have to find a way to factor in. Now, intuitively, you know that the identity of the substance would make a difference, right? If you've picked up a hot pan with a pot holder, you know that if you put your hand on a hot pan, the thermal energy transfer will be extreme and severe and it will hurt. But if you put, a thick enough piece of cotton on the pan, the thermal energy transfer into the pot holder is happening like at a much different way. It's not getting the pot holder as hot as it would get your hand, and then you don't get hurt. We have nicer ways to account for this, and that's what we're going to set up right now with this equation. So the thing that tells you about the identity of the substance is something called heat capacity. We use a capital letter C for the heat capacity. And this is the heat required to raise the temperature by 1 degree Celsius. So units are joules per degree Celsius. This generic heat capacity, you will only see it a couple of times. For the most part, we're going to deal with specific heat capacity, which is the heat required to raise the temperature of 1 gram of a substance by 1 degree Celsius. So joules per gram degree Celsius. It depends on the mass of the other object. This generic heat capacity, the way that you will see this most often is in a case where the mass has been factored in some other way. Or in lab, you might be asked to calculate the heat capacity of something when you know the specific heat capacity and you know the mass. So you'll be just coming up with a constant that represents your system as it is, and the mass is factored in, it's just kind of hidden. Since we have it with a mass value, you might also see it with a mole value. So the molar heat capacity in joules per mole degrees C. Regardless, the basics of this equation are the same. So heat is the heat capacity times the change in temperature. If you need to explicitly incorporate the mass information, because what you're dealing with is a specific heat capacity, it's Q equals m C delta T. And if you have a molar heat capacity, Q equals N C delta T. Either way, heat related to heat capacity and change in temperature. And I have some selected heat capacities here. These are usually not in the equation sheet, so if you're looking for heat capacities for working on problems, they're probably in the reading, or it's something that I would give you on an exam question. So just so you can see the range, something like lead has a heat capacity of 0.128 joules per gram degree C. Copper is around 0.4 joules per gram degree C. And then water is 4.184 joules per gram degree C. You have to put in a lot of energy to change the temperature of water. Water has a very high specific heat capacity. All right, let's look at some examples. So the first question is, how much heat is released by 240 grams of water as it cools from 96 degrees C to 25 degrees C? So almost boiling to approximately room temperature. We have a mass, and so we will need a specific heat capacity for this. So Q equals MC delta T. M is 240 grams. C sub S is 4.184 joules per gram degree C. And my final temperature was 25. My initial temperature was 96. So cooling down, I'm expecting this system to give off energy. It's going to give up thermal energy as it goes to a lower temperature. So my heat value should be negative, and the placement of final and initial temperatures is what makes that work out correctly. So I do get a negative 71,295 joules for this scenario. Now, far more often, we look at both sides of the heat transfer. So something like, I have a piece of metal, it's warmed up to a hot temperature, and I'm going to drop it in a container of cool water. I'll let it sit, and then at the end, what I will have is water that has been warmed up, metal that has been cooled down, and where they met, that temperature in between where each started, that's the temperature at thermal equilibrium. So the final temperature of the metal and the final temperature of the water are the same. But in this case, if the metal is hot and the water is cool, the water temperature is higher than what it started, the metal temperature is cooler than when it started. That thermal energy was transferred from the metal to the water. So what this means in an overall equation, whatever heat I have from the metal, it's going to be the same magnitude as the heat that's absorbed by the water, but because the metal is giving off heat, the water is absorbing heat, the signs are opposite. So I've got the negative on the sign with the water. It doesn't matter as long as one of the sides is multiplied by a -1. Let's try an example. So we have a 32.5 gram block of aluminum, which has a specific heat capacity of 0.903 joules per gram degree C. It's initially at 45.8 degrees Celsius and is submerged in 105.3 grams of water that starts out at 15.4 degrees C. What is the final temperature? Then it has this statement that's important to us being able to solve it, but it may not always be listed. But we are always going to make this assumption that the substances are thermally isolated from everything else. So we don't have to worry about the water being in contact with air and transferring thermal energy to the air or from the air. We're just going to worry about the metal and the water contained in whatever container it's in. So I've started by just making a table of the data. I think this is a good way to organize stuff from this type of problem, especially at the beginning. See what you have, see what you're missing before you start plugging everything in. You also need to include units when you plug these things in because it is extremely easy to have the units not match up. So for the metal, I know that the mass is 32.5 grams. The specific heat capacity is 0.903 joules per gram degree C, and my initial temperature is 45.8 degrees C. What I don't know is the final temperature. For water, I know the mass is 105.3 grams, but I do have a note here because you may not always be given the mass of water or the mass of a solution. We tend to measure these things by their volume. So if you're given a value in mils, you're going to need to know the density. Now, for the most part, we can assume the density of water is 1, but if you don't have water, you will need to be told how to handle the density. Now, the good news is that most solutions, if they're dilute enough, their density is close enough to 1 that we get to assume that it's 1, but you do have to know that information. The heat capacity is 4.184 joules per gram degree C. My initial temperature is 15.4 degrees C, and I don't know the final temperature. So out of all of these things, it looks like I have 2 unknowns. I'm missing the final temperature of the metal and the final temperature of the water. This is where it's required for you to know what thermal equilibrium means so that you know these final temperatures are equal to each other. So in this setup, in this scenario, between the water and the metal, I only have 1 unknown value. So whatever heat is given off by the metal, the same amount with the opposite sign is absorbed by the water. So I've got my Q metal, which is really the mass of the metal, the specific heat capacity of the metal, and the delta T of the metal is equal to the opposite of the heat of the water, which is really the mass of the water, the specific heat capacity of the water, and the delta T of the water. So I've got this initially plugged in. I am leaving delta T as it is. And I think it's easier to wait until the last minute to distribute with the algebra. So I've got this as 32.5 grams times 0.903 joules per gram degree C times delta T for the aluminum is equal to negative 105.3 times 4.184 times delta T for the water. This gives me 29.348 delta T for the metal equals negative 440.58 delta T for the water. So delta T for the metal is negative 15.012 delta T for the water. This is where I've plugged in final minus initial for each of the things and just left the final temperature labeled as TF because it's the same final temperature for both. I've done it here because now I only have to distribute on one side when I multiply through. So T final minus 45.8 equals negative 15.012 T final plus 231.19. If I add 15.012 T final to both sides, I end up with 16.012 T final equal to 276.99 after I add 45.8 to both sides. And then after dividing, I get a T final that is 17.30 degrees C. This, I can double check and see if it makes sense. So it should be higher than where the water started and lower than where the metal started, and it is, but it's also really close to the temperature that the water started, right? My water only went up 2 degrees, but my metal went down something like 30 degrees, 28, almost 30 degrees, like 28 degrees. So take a minute, ponder, see if it makes sense, why this would be the case. It should make sense, and we can talk about it when you come to class.